So far we looked at integrals with finite limits of integration and integrands that didn't have any discontinuities. Now we look at integrals that are called improper integrals, and two things happen. Either the interval over which we integrate becomes unbounded, so this guy we're going to call type 1, or the integrand function that we're trying to integrate has unboundedness occur, so function values possibly become undefined there and blow up, and that we'll call type 2. Let's go take a look at type 1 and see how it behaves. So for type 1, as we said, the interval a to b becomes unbounded, meaning one of your limits of integration, or possibly both, will end up being infinity or negative infinity. And how we deal with that is basically like if you were to look at a graph, we're interested in the area under this curve f of x from a all the way pushed through to infinity. So in part A, type 1, part A, basically the idea is that you take your integral from a to some t value. Let's say I call it t1. And you see what happens from a to t1, and then you push t1 a little bit further to, let's say, t2, and you see, okay, what happens now? Well, it gets a little bit bigger. What if I push it even further to t3, and let's see what happens there? And through this limiting process, you go all the way t to infinity and try to analyze if this region that looks infinite actually approaches a finite area or not. So your lower limit is just a constant. Your upper limit, you keep pushing further and further and further. And so therefore, when you analyze the new integral that you kind of create yourself, you just replace the treble point of infinity with some t value, and then you push that t value all the way to infinity further and further. In part B, you'll notice the lower limit is negative infinity, and I'm stopping at a finite value of b. So we replace the treble point, the infinity, with a value of t and go all the way to b. And picture-wise, graphically, what's happening here is I'm interested in this area, and it goes all the way to negative infinity. So same idea. Maybe I look at it up to here. Let's call that t1. And that's some finite area I'm looking at. And then I push it to the left a little bit, call that t2. Well, I'm dealing with some finite area. Let's push it further, t3, and that's also some finite area I'm looking at. And through this limiting process, push t all the way to here and let t go to infinity, or negative infinity in this case, and you're trying to see if this infinite amount of region looking thing actually does, through this limit process, approach a finite area, or maybe it doesn't. So like part A, all I did was replace the treble point negative infinity with t and let t go to negative infinity. So I'm taking an integral and it's turning into a limit problem once I evaluate that integral. Part C, the idea is kind of like a combination of A and B. So both limits of integration become unbounded. And picture-wise, what's going on is you're maybe looking at a region like this, going off to negative infinity on the right and positive infinity on the left. And to capture that and figure out whether it's going to reach a finite area or not, you kind of look at it like this in two pieces. So you break it up wherever you want. You can do in the middle, wherever. Pick a finite number, let's say call it A. So we look at that and we analyze this region on the left, like this problem, and we take the treble point in the bottom that was bad, t going to negative infinity, and replace that with t. And also I look at the right side, going from A to positive infinity, so a finite limit a all the way to t, and t going to positive infinity. So part C is really the type of improper integral where you see unboundedness on both ends of the limit, and all you do is you pick a finite value wherever you want where the function is defined, break it up in the middle, and go from negative infinity to a and a to infinity, thus creating two of these guys together. So you look at two different limits to analyze. So the terminology we use is, if this RHS, I'm saying right hand side, these guys on the right hand side. If the right hand side limits exist, remember this means exist. If the right hand side limits exist, the improper integral is said to be a convergent integral. That means basically that it reaches a finite number. So when you analyze the limits on the right, you actually get a finite number. You conclude that the improper integral was convergent. Otherwise, if it goes off to infinity or negative infinity, then the integral is said to be divergent, meaning the area blows up and becomes infinite. We can't actually capture it. It doesn't approach a finite value. So again, limits exist, convergent integral. Limits don't exist, divergent integral. Let's go look at some examples now. It says determine whether the integral converges or diverges. And we're looking at the integral from 1 to infinity of 1 over x squared dx. So this is clearly a type 1. We haven't even looked at type 2 yet, but you see an infinity or negative infinity in one of your limits of integration, it's going to be an improper integral. So if we quickly look at the graph, we know that the f of x equals x squared function looks something like this, and we're interested in the area from 1 all the way to the right going to infinity. So we want to see if we can capture this. Even though it goes all the way to the infinity, does it become so much smaller and approach the x-axis that eventually it approaches a finite number, or does it actually keep getting bigger and bigger and it goes to infinity? So that's what we're trying to analyze. And we're going to basically do that idea of put some t here and then keep pushing it to the right to infinity to see if we can actually capture that and the limit becomes finite or infinite. So the trouble point we're going to replace with t, and we're going to let t go to infinity. So I took this guy, I replaced it with t, and immediately let t go to infinity and look at the limit. It's important to have this all the way through on your integral when you're analyzing things. And this integrand is not so bad, it's just a power function, so let's go quickly integrate it. So we're looking at the integral x to the negative 2 dx, and again it's just a simple power function, x to the negative 1 over negative 1 from 1 to t. I'm carrying over the limit part all the way through because each time I'm looking at the limit as t goes to infinity. So let's go plug in those limits of integration and basically analyze a limit problem like we would in 261. So we look at the limit of negative 1 over x from 1 to t. I plugged in the upper limit, negative 1 over t, minus plug in the lower limit, negative 1 over 1. So now we have the limit as t goes to infinity of negative 1 over t plus 1. And again, this is simply a limit problem, like you would analyze limits in 261. Now, t goes to infinity, which means I end up with 1 over big, and that portion goes off to 0, so I end up with just the limit equaling this constant that was left, 1. So that means this is a convergent improper integral. This area, though I'm taking t all the way to infinity, actually approaches a finite number 1, meaning after a certain point, some of those values really don't contribute anything valuable, and this ends up being 1. So basically, let's quickly reiterate what convergent means here. If I'm looking at this area under the curve, graph gave us sort of an intuition that, it's possible for this guy to be convergent because the values are decreasing, but that's not always going to be the case. So what is the idea that happened here when I replaced the t with infinity? I looked at maybe this integral from 1 to x squared, and I went up to 100, and I got some number. Then I went up to 1,000, and I got some other number, probably bigger than that one because it's more area. Then I said, okay, let me go from 1 to 100,000. What happens there? I got another number. And then eventually, the bigger I made the upper limit, it approached the number 1. So the limit of all of these is eventually 1. So I went to 1,000,000, I went to 1,000,000,000, I went to 1,000,000,000. Eventually, all those values that I got under the area approached 1. That's basically the idea of this improper integral. Let's go look at another example. So the integral from 1 to infinity of 1 over x dx. Again, right off the bat, we see an infinity for one of the limits. We know this is an improper integral. We're going to start taking limit business. Now let's look at the graph to get an idea of what's happening. So remember, 1 over x is an odd function 1 over x squared before looked something like this, an even function. This has a branch in quadrant 1 and a branch in quadrant 3. And we're looking at the area from 1 to infinity. So it's a decreasing function. There is hope that maybe possibly this will reach a finite number, but we don't know. We're going to have to go analyze the limit. So immediately I replaced the trouble point infinity with a t, and I made sure I put limit as t goes to infinity. Again, let's analyze this integral, which looks like it's going to be logarithmic. So this is going to be equal to the limit that should always carry on with you. This is going to go to ln of x, and we're analyzing it from 1 to t. So I put in my limits of integration 1 and t, and we know that ln of 1 is 0. And ln of t, as t gets big, well, we know the logarithmic function looks something like that. And as we go to the right, as t gets big, this logarithmic function actually keeps growing and growing. So this guy goes off to infinity. So it looks like, although this problem looked a whole lot like the previous one, when I analyze this limit, I actually get a divergent integral because it does not approach a finite number. In other words, even though the graph looks so much similar to the previous one, as I keep going to the right, and I go from 1 to 100, I go 1 to 1,000, I go 1 to 10,000, I go 1 to 1,000,000, those values that I get, unlike the previous one that was creeping up to 1 and approaching a finite number 1, in this case, those values without bound keep getting bigger and bigger, and therefore this area region becomes infinite, and the integral is actually divergent. So don't just go by the graph where you think, oh, it's decreasing, it must be convergent. It's possible that that gets bigger and bigger without bound, and it ends up being divergent. Let's look at one more example in this video. Okay, so let's say I'm in autopilot and I look at this and I recognize it to be an improper integral because I see the infinity or the negative infinity for one of the limits of integration. Let me go replace that trouble point with t and see what happens. Okay, so now I got a trouble point replaced with t, and I have e to the negative 2t dt. I know this is a t and this is a t, so not to make things confusing, doesn't really matter, but let's call this guy, I don't know, a v, so that the variables are different. So I just replace the trouble point with v, and I'm going to let v go to negative infinity, and then just analyze this really quickly. So remember, that's a quick u sub, e to the negative 2d goes to e to the negative 2t divided by negative 2, whatever that constant is. Let's go plug in the limits of integration. So I just put the negative a half outside, and I have e to the negative 2 plug in the negative 1 for the upper limit, and e to the negative 2 v for the lower limit. And now we're going to look at what happens when v goes to negative infinity. So this piece is just e squared, negative 1 and negative 2. And for this piece, remember, I'm putting in and evaluating something approaching negative infinity here. So it looks like this guy is actually going to end up being e to the negative 2. If I think of putting in something negative big, it's actually going to be e to the really big infinity. So this piece is constant, but this piece is going to blow up, and it's a negative value. So it looks like this thing is going to go to negative infinity, and this integral actually becomes divergent. So again, since this was a negative infinity and a negative became positive, e to the big blows up and becomes divergent. It was a negative in the front, so it's going to be a negative infinity. Now let's go quickly look at the graph of this thing to get an idea if this kind of makes sense, because, you know, not always, but sometimes we get a feel of it by looking at the graph. So we know e to the t looks like the exponential function, e to the negative 2. T is flipped about the y-axis, and this guy says, look at the area from negative infinity all the way here up to negative 1. Well, if we had just looked at that before we did the integral, we would have clearly seen this guy has got to be divergent, because look at that region, that thing keeps going up, so that region, of course, is not going to be a finite amount that we're going to be able to capture, so this integral for sure is divergent, because we were looking at it from negative infinity all the way up to negative 1 based on the limits of integration.